For this lesson, we are going to wrap up, at least for the time being, our discussion of transformations of functions. So this lesson is going to act as something of a summary, but I'm also going to introduce another concept that you probably have not seen yet, and that is known as the mapping rule, which can be quite useful under certain circumstances. If you have a transformed function, which I presented here in what is the most standard form for a transformed function, notice that here the function is f, but we don't actually know which function that is referring to. And we don't actually care when we're talking about transformations in general. It can be just this generic transformed function. Similarly, a, k, p, and q, that's one way to represent the different parameters that represent those transformations. But I've also seen representations where you see a, b, c, d. They're just letters. The important thing is the concepts that they are trying to tell you about. Reading from left to right, the first one we encounter is A. The A parameter is going to tell you about vertical reflections, so reflections in the x-axis, and any scaling, which means making it bigger or smaller, stretching or compressing. All of those operations are multiplication operations, and specifically they are multiplications of the y-coordinate. So if we think of this in terms of a point, a y-coordinate turns into that same y-coordinate multiplied by whatever the a value is. Continuing from left to right, now we go inside the function bracket. Standard form is going to have it in this factored form, where the coefficient of the x or of the independent variable is 1. So if you've got it written that way, then your k value, it's very similar to the a value, except for now it's representing a horizontal reflection, and it also takes care of any scaling, stretch, or compression. By this point, you should be familiar enough with what that scaling looks like and realize that when we have big numbers here, for example, if I had 5 there for k, that would actually mean a compression. And if I had 1/2 for k, so a number less than 1, that would actually mean a stretch. And algebraically, the way that we represent that is we actually take our x-coordinate and then we take it and divide by k. X divided by 5 turns into a smaller number. That's a compression. X divided by 1/2 is actually the same as multiplying by 2. That turns it into a bigger number. And that's part of the way to keep straight about the idea that a big number here results in actually a compression, a smaller result. Continuing left to right, we get to our x minus p. It is important that it's thought of in this form, x minus p. That's the standard form. And that p parameter tells you about a horizontal shift to the left or to the right. Now, instead of multiplication or division, a horizontal shift is going to involve addition. So my x-coordinate, because it is a left-right operation, is going to become x plus p, assuming that it was written in this form, x minus p in the bracket. And then our last transformation, which is represented by the parameter q, that's a vertical shift up or down. And that is once again an addition or subtraction where the y-coordinate changes into y plus q. If we put all of those things together, we can create what is known as the image point or the mapping rule. I think I usually refer to this as the mapping rule, but I believe the textbook that we are currently using makes reference to image point. What this is telling you is that any point on your original graph, xy, is going to be transformed into a new point, which is going to be x divided by k plus p, that's the new x-coordinate, and ay plus q, that's the new y-coordinate. It's also worth pointing out, because they are so important, it is also worth pointing out what happens to asymptotes. Now, asymptotes, the ones that we've dealt with so far, The asymptotes we've dealt with have been, for example, vertical asymptotes. Well, actually, those can be at any value. We've encountered some different places where you can have vertical asymptotes. Horizontal asymptotes, we've dealt with y equals 0 so far. You'll get into more complicated ones, particularly in the grade 12 course. But the important thing to remember is that whether it's a vertical asymptote or a horizontal asymptote, and these numbers C and D, I've just put them there as placeholders for numbers, you use the exact same operations from the mapping rule. So if you have a vertical asymptote, which has the equation of a vertical line is x equals c, then you would transform that number c, and that's going to give you your new vertical asymptote. And if you have a horizontal asymptote, the equation of a horizontal line is y equals d, y equals some value. You're going to transform that just like you would a y coordinate, and this is going to give you your new equation for your horizontal asymptote. Let's put this into practice. So given the following transformation and these parent functions, first of all, let's identify the transformations. Then we're going to write out the mapping rule. And then we're going to write out our equation in what's known as XY notation. So we're actually going to make the substitution of the function and turn it into a recognizable form for the function. But to start, we will just focus on the generic form because we can use that for both A and B. Reading from left to right, I haven't done anything fancy here. I'm not trying to trip you up. I think I will include a way that I could have tripped you up, and not intentionally. It's something you just need to be aware of. So I'll get back to that in a moment. Hopefully I'll remember to circle back around to that. So let's identify the transformations. I've given this to you in standard form. So that A value, that's A equals 3. That's our first parameter. And A equals 3 tells us that we have a vertical stretch by a factor of 3. The next parameter, reading from left to right, is my K value, which is a half. And that represents a horizontal stretch by a factor of 2. Because 1 over 1/2 is the same as 1 times 2 over 1 is equal to 2. The next parameter, now don't forget this is by default x minus p. And so that actually tells us that our p value itself is 2. And that means we have a horizontal shift right by 2. And then finally, I have, normally this on the outside would be plus q, but you can see that's minus 5. So that actually tells me the q value itself is minus 5. And that is a vertical shift. And in this case, it's a vertical shift down by 5. So those are the transformations. Now, the mapping rule. In general, the mapping rule, and I think it's really worth it for you to commit this to memory, or if you have a good enough understanding of what the transformations mean, you shouldn't have to, strictly speaking, memorize it. It should actually make a certain amount of sense to you. The x-coordinate is going to be divided by k, and then we add p. The y-coordinate is going to be multiplied by a, and then we add q. Now, in our case, we actually know what some of these, well, we know what all of those parameters are. So instead of x divided by k, I'm going to write that as x over a half plus p, which is plus 2, and then a, which is 3 times y, and it would be plus q, but since we know that it's a shift down, I'm just going to go straight to minus 5. And then I'm going to simplify this a little bit. X divided by a half is the same as 2x plus 2 for the p value, 3y minus 5. Now I'm going to, at this point, I'm going to make a slight aside, which is I'm just going to remind you of what the original transformed function looked like. And I think I have remembered that correctly. 3f of 1/2 x minus 2 minus 5. I could write this in another form, and it would no longer be what we consider to be a standard form, which is I'm actually going to expand and simplify this inner bracket. 1/2 times x is 1/2 x, and 1/2 times -2 is -1. And you can see, of course, that if you look at this, it does not match the transformations that we went through. In particular, it's quite glaring that the p-value is not there, it's not the same. And it's the way I said it first is actually more appropriate. This is no longer p, okay? And the reason is because p is defined when you have it in this form specifically. So when we talk about that p-value, it has to be in the form x minus p, where the coefficient on the x is 1. Here, the coefficient on the x is 1/2. So this is not the p parameter. Now, there is another way of dealing with transformations, and I know that there are some math teachers who really prefer it, and it's called input-output diagrams, or input-output tables, maybe it might be referred to as well. And it's another technique, and it works. And one of its big advantages is it doesn't care what form you're in here. The way you do input-output diagrams, it actually deals with this quite nicely, and it's one of the major advantages of it. But I do teach it this way because I have found that students adapt to this a little bit better. But if you're curious, you could go look that up for your own edification. So I did want to mention that to you. If you are ever given a question that's in this form, it is incumbent upon you to recognize that it is not in what we call standard form, and then you must make the change. You must factor out that leading coefficient. And I can't promise you that I won't give you, or that the textbook won't give you, questions that are in this form. It's not typical, but it absolutely does happen. Okay, so now moving on from that little bit of a warning and a little bit of an extra layer of subtlety, write the transformation in xy notation. Well, what if f of x is the square root of x? And it's actually good. I've rewritten my equation here. So now what if, for part I, the first one, f of x is equal to the square root of x? Well, we have function notation that says I've got 3f of, and then the first thing is inside this square bracket, that's what goes inside the square root. So I'm going to write 1/2 times x minus 2, but I know that part is entirely inside the square root. And then multiplying, now we're done with the f of x part. Wherever there was an x, I've replaced it with what was inside the bracket. And now I've got a 3 in front, multiplying it, and I have to put this -5 on the outside, and it has to be very clear that the square root ended here and the -5 has nothing to do with the square root. The second one I wanted to consider in this way is 1 over x. So what if f of x instead is 1 over x? Now, to put that into xy notation, well, it's 1 over whatever was inside the bracket, which was 1/2 times x minus 2. In front of this whole thing is a multiplier by 3. And then outside of the whole thing, which the whole thing I'm referring to here is the rational function, is the shift down by 5, or the -5. Now, the first one I couldn't simplify in any meaningful way, but this one I absolutely can. First of all, I've got 1 divided by 1/2. 1 over 1/2 is just equal to 2. But I also have this 3 in front of the bracket, which is the same as 3 over 1. So we get numerator times numerator, and we get 3 times 1, and then over 1/2 is the same as times 2. So the new numerator is actually 6 over, and now I've taken care of this 1/2, and I turned it into a 2 in the numerator. X minus 2 is all that's left in the denominator, so now I don't need a bracket around the denominator. and I have a minus 5. So even though we were in this standard form and we had very clearly defined transformations, in this case, our xy notation, simplified, it looks quite different. But what that tells you is that the new transformations that go along with this form are actually equivalent to the transformations we had in the original form. If you were to graph A and B here, if you were to graph these separately, you would, of course, get the exact same result if you graph those using a table of values or if you graph those using technology. Okay, so that answers that example. Let's go on to what I believe is the last example for this fairly short lesson and note. So here is an example. The points -4, -2, and 3, +2 are on the graph of y equals f of x. Notice I'm not giving you f of x here. We have no idea what this parent function looks like. All we know is that it includes these 2 points. There may be other points, there may not. It doesn't matter. Determine the new points on the transformed graph, and you can see I have a fairly elaborate transformation here. These 2 points that are provided to you are going to turn into 2 new points. They're going to be transformed. So the first thing, and I think it's a good idea to actually write it out. So I'm going to write out the mapping rule for this. I'm going to recognize, and since we talked about it, I'm going to recognize that this is indeed in our standard form for function transformations. So I know the point xy, the x coordinate is going to go to x divided by k, which is x divided by 1/4, plus p, but remember, it's supposed to be in the form x minus p, so that actually tells me that the p is -3. This is a shift to the left by 3. And then ay is going to be -2 times y plus q, which in this case just stays. I don't want the letter q there. I want the number 2. And I'll just simplify that a little bit. And actually, you know what? I used the wrong symbol here. That's not supposed to be an equal sign. It's supposed to be an arrow. The point xy is going to become this new point, but they're not the same points. I can use an equal sign over here because I'm just simplifying my mapping rule, and it turns into 4x minus 3 and -2y plus 2. So what about the first point? -4, -2 will turn into, and now we sub, wherever we had an x, we replace it with, so it's going to be 4x minus 3, but I'm going to replace that x with -4 minus 3, and then it's going to be -2 times y, which is -2, plus 2. And what does this point turn out to be? 4 times -4 is -16, minus 3 is -19. That's the new x coordinate. And then -2 times -2 is +4, plus 2 is 6. So -19, 6 is the new point. -4, -2 turned into -19, 6. What about 3, 2? Well, that becomes 4 times 3 minus 3, and -2 times +2, that's the replacement for the y coordinate, plus 2. And that new point is 4 times 3 is 12, minus 3 is 9. -2 times 2 is -4, plus 2 is -2. And that's all you would really need to write here. It's quite clear from the notation that I've used that the first point turned into this first transform point, and the second turned into this one. Now, what if you wanted to go the other way? What if you wanted to reverse this? The way you reverse it is you have to reverse everything. So we've learned about function inverses, and that's kind of the same idea. So if we want to reverse this, we have to reverse our operations, And hopefully that part is the part that would have occurred to you. Where I used to add, I now have to subtract. Where I used to multiply, I have to divide. But this is the part that students often forget, is you also have to reverse your order of operations. And so in the case of, let's say, the x-coordinate, 4x minus 3, I multiplied by 4 and then I subtracted 3. So 4x minus 3 reversed is what? 4x minus 3. What's the opposite? The opposite of multiplying by 4 is dividing by 4. The opposite of subtracting 3 is adding 3. But I have to do this in the reverse order. So I'm going to add 3 first, and then I'm going to divide by 4. Negative 2y plus 2 reversed is, well, what did I do? The last thing I did here was add 2. So the first thing I need to do is subtract 2. And then the first thing I did was multiply by negative 2. So now I'm going to divide by negative 2. Notice also there that the negatives, that's unchanged. So let's take that last point. Let's give myself a little bit more room. If I take that last point, 9, negative 2, it's going to become, now I take 9 plus 3 and divide it by 4. And I take negative 2 for the y-coordinate. That's going to become negative 2 minus 2 divided by negative 2. And what does that equal to? 9 plus 3 is 12, divided by 4 is 3. Negative 2 minus 2 is negative 4, divided by negative 2 is positive 2. And of course, that is the starting point. So 3, 2 turned into 9, negative 2. And if we reverse all of those operations, we take 9, negative 2, and we turn it right back into 3, 2. But the key there is reversing order of operations as well as the actual arithmetic. That is it for this particular lesson. I've got a bunch of specific instructions for our current textbook's questions, just because I want you to be practicing a variety of skills, and the textbook doesn't give you the specific direction that I would like you to have for these. So please keep those specific directions in mind if those are the questions that you're doing for your homework.